Good evening. Welcome to our lecture series of Puya. Tonight, we are honored to have an eminent professor, a great scholar, and a scientist as our guest, namely Dr. Azadeh Ansari, professor at Georgia Tech, for which we are grateful to our dear friend, Dr. Hamideh Garmestani, who is a distinguished professor at Georgia Tech and a member of the board of Puya, as well as Kanoon. As you know, Puya stands for Professional Organization of Iranian Americans in Atlanta. Puya is an affiliate of Kanoon and is a non-religious, non-political, and a purely independent organization. I have the honor of being the president of Puya, which has a board of directors different from that of Kanoon. The lectures are all in English so that our Iranian American generation 1.5 and 2, who unfortunately do not know Farsi, can benefit from them. Puya works tirelessly to uphold the three pillars of its mission. Number one, to provide an opportunity for Iranian American professionals to network and support each other. Number two, to help the next generation of Iranian American professionals to succeed and prosper. Number three, to promote a positive image and counter the negative media depiction of Iran and Iranian professionals. Please support Puya by donating via puya.net. Now I will introduce our honorable speaker for tonight. Dr. Azadeh Ansari is an assistant professor at Georgia Tech, Georgia. She received her BS degree in electrical engineering from Sharif University of Technology, Iran in 2010. She earned her MS and PhD degrees in electrical engineering from the University of Michigan, Ann Arbor in 2013 and 2016, respectively, focusing upon semiconductor and microelectrochemical devices and microsystems for radio frequency applications. Prior to joining the electrical and computer engineering faculty at Georgia Tech, she was a postdoctoral scholar at the physics department at Caltech from 2016 to 2017. Dr. Ansari is the recipient of a 2017 ProQuest Distinguished Dissertation Award from the University of Michigan for her dissertation of gallium nitride integrated microsystems for radio frequency applications. She received the University of Michigan Richard and Eleanor Tower Prize for Outstanding PhD Dissertation in 2016. She's a member of the Institute of Electrical and Electronic Engineers, IEEE, IEFCS, Institute of Foreign Credential Services, IFCS, in 2018. Dr. Ansari, it's an honor to have you as a speaker at Puya tonight. On behalf of the board of Puya, I extend our most sincere gratitude to you. Dr. Ansari will talk about recent advances and outlook in microscale robotics for biomedical applications. And we are all ears, Dr. Ansari. We are very eager to hear what you're going to say tonight. Thank you.
Thank you. Thank you very much for the kind introduction. And it's my honor to be presenting some of our research to this lovely community. So thank you for inviting me. So let me go ahead and share my screen. I hope everyone can see it, right? Okay. All right. So today I will be talking about recent advances in microscale robotics. So my research is focused on making tiny devices that are between mechanical engineering and electrical engineering used for sensing applications. A lot of these devices go into your cell phones for communications, sensing like accelerometers and gyroscopes. But also another thread of my research, which I've been doing ever since I joined Georgia Tech, is building small-scale robots with fabrication techniques that are used to build computer chips. So very similar to the fabrication techniques that have been going on for many years for building microcontrollers, chips, and electronics. And today I will focus on the biomedical aspects of these small-scale robots. So let me go ahead and just share some of the application spaces of this research thread. So I'm a director of a center that is supported by Georgia Tech Institute of Electronics and Nanotechnologies. And one of the research threads for these small-scale robots is for surgical applications. So I will talk about this thread. Basically, we collaborate with a neurosurgeon at Emory University, and we are developing tools that can basically help the surgeons tackle and access tumors that are deep in the spaces that normally, if they want to access, they may damage other otherwise healthy tissue or not have direct access to them. So I will talk a lot about these tools that look like a little driller, right? But in very, very small scale. So with footprints of hundreds of micrometers. Next, another thread of research in my group, which I don't think I will have time to cover today, is supported by NASA, and that's work to explore the space using, again, very small robots, but many, many of them. So the scientists have basically discovered water under the icy moons of some of the planets. And wherever there is water, there is sign of life. So they're very interested to see if they can detect any, molecules that can be a sign of life. However, to get to the moons, to those icy moons, and penetrate through kilometers thick sheets of ice is not easy, right? So they use a melting probe to basically melt the ice to get to the water underneath the ice. And once you get there, if you just have a big robot, you're limited to the volume or to the space that you can explore. Instead, if you have many, many smaller robots that you can dispatch and let them sense and communicate with a central unit, then you can basically extend your area of exploration and be more efficient in sensing, the temperature, the pH of the water, right? All the salinity and some chemicals that they're interested in. And then finally, another thread of research is using vibrations, right? Vibrations, the same thing that moves the air molecules to produce sound. Can we use vibrations or even ultrasound frequencies to move robots? So that's something that I have been working on. We use piezoelectric actuators. So that's the same thing as the buzzer when you press and you hear a sound. So the same technology can be used to actually move robots in air and in water as well. And then finally, I'll talk about what happens when you put many, many of these small robots together. So this, this image here kind of resembles the colony of ants maybe, or, when you have smaller robots, you can basically pack many of them together, and a lot of interesting behaviors will emerge once you use this, plurality of robot instead of having one super smart robot. So a bunch of little less smart robots could be helpful in that sense. So let me start by going back to this Richard Feynman's classic talk. So Richard Feynman is an American theoretical physicist who got the Nobel Prize, and basically he coined the term nanotechnology. So he had a very famous talk, which was called "Plenty of Room at the Bottom" back in 1959, where he talks about, scaling things down, going and actually coining the word nanotechnology. And then 25 years after this famous talk at Caltech, he gives another talk called Tiny Machines. And at that point, this electronic nanotechnology and MEMS sensors were not as mature as what they are right now, but he envisions that we can have microelectromechanical sensors and devices. And finally, he asks the audience, can you think about writing the whole, Encyclopedia of Britannica on a head of a pen, right? So what takes to write things down in such small scales, and can we store things in a very, very small, scales? And, right now we know that we can do that. So we have surpassed what we thought we could do. However, on the actuator side or small scale robots, so he talks about tiny machines and says, can we actually swallow a surgeon? And think about a little robot that can go inside your body, either for therapeutics or even diagnostics, and find out what's going on wrong. Can I cut something and come back, take a biopsy, send something? So he just, basically at that point, just envisions what happens if we can swallow a surgeon, right? So I'll just go over this text from Richard Feynman, that he says, a friend of mine suggests a very interesting possibility for relatively small machines. He says that although it's a very wild idea, it would be interesting in surgery if you could swallow the surgeon. You put the mechanical surgeon inside the blood vessel and it goes into the heart and looks around. Of course, the information has to be fed out, right? So you need some sort of communications with the outside world, obviously. It finds out which valve is the faulty one and takes a little knife, slices it out. Other small machines might be permanently incorporated in the body to assist some inadequately functioning organ. Now comes the interesting question, how do we make such tiny mechanism? I leave that to you, right? So today I will be talking a little bit about the fabrication techniques of making super, super small robots that could be used for biomedical applications. And then some years later, 1966, there's this American sci-fi movie called Fantastic Voyage, which is, it basically revolves around a scientist who has some sort of a blood clot in his brain. And then basically they shrink like a little submarine that goes into the blood vessels and helps declot the clot that is happening, and the scientist basically is cured. So that's just to tell you that the idea has been out there for a long time. Now, on the fabrication techniques, since my research is very much experimental and we basically build these small scale devices at the Georgia Tech Clean Room. So I want to show you a few devices that have been fabricated using recent advances in nanofabrication. So here on the top left, for example, what you can see looks very much like two guitar strings, right? So we know that when we ping a guitar, you will hear a tone at a certain frequency in the audible range. Now, when you scale things down in the nanoscale regime or in micro nanoscale regime, we still basically, if you ping a beam, like what you can see, right? There will be a frequency that will be produced, but that would be much, much higher than the audio signal. So we can't hear it anymore. However, you can pick it up if you have the right tools. So this is very much used actually for communication purposes, for 5G, wireless communication. Very similar technique to the guitar string is used. And these devices are very, very thin and small. They have a very small footprint, like 1,000 times smaller than a hair diameter. So you can think of, what these scales are. And these devices in particular are built using electron beam lithography, which is a, advanced tool that is used to make tiny layer by layer, basically, tiny devices. And then we have other types of lithography and fabrication. So these are self-assembled hollow cylinders. This other example basically is used for, again, biomedical applications. So it's like some metals that are basically not 2D anymore because of the stress in the thin film that is causing it to basically stand up like it is. And then on the bottom left, you see a 3D printed structure. So nowadays there's a lot of, research going on in the 3D printing area. However, making them small and fine resolution is still a challenge. So we use a technique that is called 2-photon polymerization that allows you to 3D print things with a resolution of 100 nanometer. So this is very powerful. You can, draw any arbitrary pattern using this 2-photon polymerization technique. And basically it's mainly made of polymer, so it's a little hard to have multi-materials, but that's all ongoing research. So using these techniques, let's see what kind of little robots are out there, right? So this is one of the original works in the field of microrobotics from ETH Zurich. So what they've done here is that they basically 3D print these little spirals, right? As you can see, or they call it the helical microswimmers. After they fabricate these, they coat it with a magnetic material. Now, the good thing about a magnetic material is that if you have an external magnetic field, you can manipulate the robot with the magnetic material on it to basically do the things that you want it to do, again, using your external magnetic fields. So these are helical microswimmers, and I'm going to play this video. So this is in a liquid environment, and as you can see with the external magnetic field rotating, and these guys can actually basically carry a load and transport it and then drop it at the place of the place that you want. And again, bear in mind the scale bar is 100 micrometers, right? So this 100 micrometer is roughly the diameter of your hair. So these are, again, super tiny microscopic robots that can actually do things, right, without you directly using basically your hands, right? So you're just controlling the magnetic fields, letting the robot do its thing. And then, these all seem very interesting. However, there are some challenges with these very small robots. One is, if you wanted to do anything useful, you probably want some sort of sensor to be attached to it, right? For example, in the biomedical application or in vivo application example, like, do I want to sense a pressure? Let's say I want to sense the pressure of my eyes somewhere, right? Or I want to have a sensor that senses the stiffness of a tissue to see whether it's tumor or it's a healthy tissue, right? So you want some sort of sensor attached on your robot, and those take up space, right? Then you need some sort of computation. How do I communicate, right? Let's say I found something that is faulty, right? How do I communicate with the external world? Do I want to put a Bluetooth and antenna, right? These all take a lot of space. So we want to think of what is the smartest way to make these smaller and still be functional. And then batteries are most of the time out of the picture because they're very big, right? So you would prefer to have some sort of external powering, like use magnetic fields, use ultrasound transduction, vibrations, optical laser, something that is outside so that you eliminate the battery itself. And then controls, right? So that the precision and the control of where these little guys are going, of course, is very important. And then obviously what applications come to your mind, like almost, a lot of biomedical applications are a lot that can use these small robots basically inside the human body. And some of the other work that have been very recent, so this is a Nature paper published, I think in 2020, 4 years ago, and they basically use a little robot using exactly the same techniques as you use your microchips. So, no fancy 3D printing technique, really layer by layer lithography. And then they shine a laser at these legs, and that causes some heat, right? And then when the thing gets heated up, the stress is basically manipulated and causes the little legs to get actuated, like what you can see here. However, applying a laser, for example, for it needs a line of sight and has its own disadvantages. Nevertheless, it's a pretty cool demonstration of what can be done using standard fabrication techniques. Now, thinking holistically about biomedical micro robots, let me show you this chart, which says, I asked the question, or that was mostly Richard Feynman's question, of how do we make these tiny machines? So making them is one thing. It's not everything, right? So what are the other challenges in this field? So one is the actuation and the controls. As I said, like actuation, you may need magnetic fields, you may need ultrasound, optical, a laser, something that generates heat. So you have to think about these the actuation and also the controls, right? You want to know exactly where your robot is at any given time. You don't, so that the controls becomes important. The other thing is compatibility with medical imaging modalities, right? Do I have an MRI or a CT scan that tells me exactly where this robot is located? I may not care too much where it is, again, depending on the application. However, the robot, given that the size is very small, needs to be compatible with some sort of medical imaging modalities. And then permeating biological barriers, what kind of medical functions, deployment strategy, do I eat it, do I swallow it, does it get injected? And then how do I retrieve it, right? Is it biodegradable? Does it degrade over time, or do I need to retrieve it? Do I need surgery to insert it, surgery to remove it? Or, so you can think about all of these different aspects for designing a biomedical robot. So let me just see, what do we have here? So I think I covered, it did cover most of these bullet points here. So with that, I think, let me go over some of the examples of what is currently available. A little bit on the larger scale. One is this capsule endoscopy. So this capsule, basically you can take it. It's a little big. It's got a little camera inside it, right? So this is, again, commercially available. You can purchase these, especially, if you don't want to go through endoscopy, which may be a little uncomfortable and inconvenient. So these are right now about 2.5 centimeters in length, 1 inch. Once you swallow it, basically you don't have control. You just rely on your digestive system, basically, to let it just take images as it goes on, and then you can have a belt around your waist to collect these images. So this is a pretty compact system that has got the full sensing, communications and all of that. Again, a little bit on the bigger size, 2 centimeters, still pretty big. And then there are these thermal microgripper. So these guys basically do this, right, when they get heated up. So you can use these pill cam, or these basically capsules, and then load them with microgrippers. When the temperature goes up, these guys, start basically getting actuated, and they can collect basically payloads and, transport, deliver. So this is one extended application of these capsules that can hold these thermal microgrippers. This one is a research topic. So this is, I don't think it is commercialized, is using ocular drug delivery. So again, accessing the back of the eye is very difficult. If you, for example, for drug delivery, you have to rely on the diffusion of these drugs, and you may not be able to target the drug to the specific location. So they use basically these little swimmers, again, to swim around your eye, and you can have magnets around basically your eye, and basically control these swimmers to go to a specific location and then release the drug, right? So these have, this is also work out of ETH Zurich. So Europe somehow is doing much better than the US, I would say, in this particular topic. Anyways, so these are just some of the examples that are out, not from my group, but from other groups. So with that introduction, I would like to start talking a little bit about the research that has been ongoing in my group. So the first one, as I mentioned, is these little drillers that exactly look like a drill bit. And you can see in this picture, basically, this is on a US penny, right? So I think you can see the scale of these little drillers compared to the US penny. And if you feel bad about having this inside your brain, our neurosurgeon collaborator says that the patients don't know what we do when, you know, when we're doing the surgery. It's very brutal, right? The tools are all very traditional, and I'll talk about that. So this is actually, even though, you know, it's like a little magnet going inside your head, it can still be less intrusive than the traditional methods. And then the other topic is these vibration-powered micro robots that just use, you know, ultrasound or vibrations as their actuation mechanism. And then finally, I'll talk a little bit about what happens when you put a bunch of these together that resembles, you know, these swarms of ants or the school of fish, or all of these that are inspired from nature, right? So this swarm behavior that we have out there in nature, but can we use that to make smaller robots that are, again, less smart than a bigger one, but through communicating, let's say, with the neighbors, or through using these emergent behaviors, they can do more powerful things. And then finally, I will talk a little bit about micro robots that we use for 2D, basically 2D motion control, mostly for like lab on a chip applications and so on and so forth. So let me start with this neurosurgery application. Again, all of this started for me when a neurosurgeon at Emory, Dr. Kimberly Huang, contacted me, and she said, you know, we really want to develop something that helps the surgeon access tumors that are deep-seated. And she was telling us that when they do surgery, a lot of times after the surgery, the patient loses some part of their functionality. For example, they can't speak for a while, or, you know, some healthy tissue gets damaged when the surgeon tries to access a deep-seated tumor. And again, the tools are pretty classic. They are, you know, there's a bit of robotics, surgical robotics going on, but still pretty bulky and not a very good path forward accessing deep-seated tumors. So the idea here was, can the surgeon, basically like what Richard Feynman was saying, stay outside, hands off, right? And they can control this little robot and tell it to go from point A in the brain to point B in the brain. Now, the brain is a very complex structure, right? You have, you know, you have a fluid, CSF, you've got the tissue itself, and then there are these air gaps and holes, you know, gyri, and, you know, all of these interesting, complex shape that it has. But can we come up with devices that can actually travel in any nonlinear trajectory and do something useful? For example, again, deliver a drug or take a little biopsy and bring it out. So this was how we started collaborating and thinking about this. And then we had one of the works that we did was basically 3D printing this drill bit, which looks very much like an actual, excuse me, drill. But there's a tiny magnet attached to the back of this drill. So when you have magnetic fields, this guy can rotate, right? As it rotates, it basically shears through the tissue and penetrates inside the tissue. So this is how we fabricate it. We put the magnet first, and then we do that nanoscale 3D printing or the 2-photon lithography on top of this magnet, as you can see. And in this particular example, we have a little backpack basically for this robot that has a hydrogel, and I'll talk a little bit more about what is interesting about this hydrogel. But basically, you can load it with drugs, and when the pH of the environment changes, the hydrogel will release the drug, right? So I'll talk about what that means. And then we control everything with external magnets. So the idea is that there will be, you know, some like you can think of a helmet, right? Some magnets maybe around the head of the patient to control this little drill bit. So here we are showing basically how this little robot looks. So this is a video. So my student is controlling this with a joystick, and he's trying to write Georgia Tech. Now, it's a little rough at some edges, but the robot can actually turn and move around. And this is inside a hydrogel that resembles the brain in terms of its stiffness and mechanical properties. So people use agar gel as a phantom instead of using brain. It's transparent, so you can see what goes through, but mechanically it's very similar to the brain. And the magnetic fields that we use are pretty small. So this is 10 milliteslas. For reference, MRI uses a couple teslas. So this is not a very large magnetic field that, is used to move this. And then we tried this in different agar gel and concentrations, characterize the speed versus the frequency, the angle of rotation, and basically the controls aspects of these robots. And my graduate student actually won a best paper award in a microrobotics conference for this work. And then a little bit more about the hydrogel part. So apparently tumors are a little more acidic than healthy cells. So their pH is different. So the idea here is that when a driller goes into an environment, if it's more acidic, it releases the drug much faster than in a less acidic environment. So, and this basically difference is very small. The pH 6.2 versus 7.8, and you can see a pretty drastic change in the release of the drug or in its diffusion versus different pH values. So ongoing work is further miniaturizing these because we want to minimize tissue damage as much as possible, right? So the smaller, the better, obviously. So we're looking to make these a little less invasive, optimizing our coil system for larger areas, right? Starting maybe with a pig head or a mouse head, that's even smaller, and then moving on to an actual human size head. And then testing and imaging in actual brain tissue. So right now we're testing these in phantoms or gels that resemble the brain but are not actual tissues, and co-developing a coil system that is compatible with an imaging modality such as a CT scan. And this is also some work that we are collaborating with another professor at Emory, Dr. Morteza, who works on CT scans. So this work is basically we are using different metals on this little robot, and they have a specific type of a CT scan, which has higher resolution photon counting CT scan. And when we use two different types of metal, they're able to distinguish between the two. So you can basically know the direction of your robot. Let's say if you have tungsten on the top and neodymium on the back of your robot, right? So you want to know basically where your robot is pointing at. And the system has a good resolution and lets you know what the direction of this robot is. So this is ongoing work, obviously. This is basically an actual CT scan image inside a skull. But we're looking to further miniaturize these devices and still be able to resolve them with imaging modalities. All right, so I'm going to switch gears a little bit and talk about vibration-powered microcrystal robots. So this is the work that I first started when I joined Georgia Tech. So here we have a little vibrating robot, and how it works is that we have a piezoelectric actuator. Again, this is the same thing that you use in a buzzer or even the lighters when you press and you can generate electricity. It's a conventional way to convert electrical energy to mechanical energy and vice versa. So how these works is that generally these guys, if you apply an electric signal to them, you can get some motion out. And you can use that motion to move a robot, right? And these are basically 3D printed legs, so little bristles like, little legs. nanoscale 3D printed. And when you turn on an external vibratory signal, you can basically move them around. And what we did is that we started designing different types of legs, playing with the angles of the legs. And again, these are 3 of the robots on a US penny, just for the reference of the sizes. And let me show you, well, let me show this, and then I'll show a YouTube video. So we play with the leg designs and try to see if that affects the motion of these robots. And here you can see that, you know, some of these angles work better than the others and have faster speeds and better directionality. So we looked into this to see what is really going on. And it turns out that there is this resonance behavior, again, very similar to the tone that a guitar string can make, right? So at a very specific frequency, the legs of these robots respond to that frequency, and they don't respond to any other frequencies. So what we do is that we design different robots that have different resonant frequencies. So when we apply that particular tone, they get actuated, right? So that was kind of the beauty of this work, that you can selectively actuate different robots by tuning to the correct frequency. And this work basically got a lot of attention. It was covered in Nature Electronics, and then some of these, you know, pop media, scientific, papers. So this one is saying, sorry, Wall-E, this is now the world's cutest robot. And this was, you know, again, our little tiny robot compared to the US penny. And let me show this YouTube video from Georgia Tech. Let me make sure. Oh, okay, here. I hope you can all see. So let me go back to the slides. So once we had one little robot that could basically move in at a certain frequency, we thought, how can we control it, right? Can I make it move right, left, forward, backward? How can I make that possible by just changing the frequency of the actuator, right? So we had this little PZT this time on top of the robot, and we started changing the frequency, and we were able to see that at a very specific frequency, the robot moves forward, and at another very distinct frequency, the robot moves backward. And these frequencies would differ if the angle of those little legs would change. And theoretically, we were able to basically prove that with, dry friction models, that you can predict this forward and backward region when you change the frequency. And the motion is basically called stick and slip. which I'm not going to go into much detail. And then the next idea was, can I have asymmetric legs such that at one frequency, only one set of the legs move, right? Because we're hitting the resonance frequency of one set of the legs so that you can turn effectively in one direction. And at the other frequencies, the right side of the robot moves while the left side is anchored so that you can move to the left part, right? So theoretically, if you can selectively actuate the left side and the right side of this tiny robot, you can make it move in different directions. So we worked on this basically concept, and we were able to show steering of this robot when we were changing the frequency. For example, at 49 kilohertz, so this video is muted, otherwise you would have heard this. It's not a very pleasant sound, but it was moving forward. You change the frequency a little bit, then it starts moving backward, right? And further, we could make them turn or move left and right again by another set of frequencies. And if you mix these frequencies, which is part 2, you can basically cover this whole 360-degree 2D plane. So this is, and these are all open loop. So basically, if you use closed loop controls, obviously you can have very precise X, Y, Z, or X, Y, this is 2D, X, Y control over the location of the robot. So this is just some characterization of showing, at each frequencies, where does the robot move and how can we cover this full 360-degree 2D plane. Now, once we basically looked at these individual robots, we wanted to put them together and see what can we do. And remember, these robots do not have any sensors on them and they do not communicate with each other. So they're basically like particles bumping into each other. And we wanted to see, can we use that, basically the collision of the robots to control them to aggregate and disperse, right? By just changing the frequency and the amplitude of the external vibration. So here we partnered up with some roboticists or a few of our roboticist colleagues at Georgia Tech, who were responsible for the modeling and basically the algorithm part of this, and we were making these robots for them. So here we put 300 robots with little legs, and we put them all basically on a table that just shakes up and down. And I think this video, let's see if it plays or not. Let me just go to the Google Chrome link, because this always has issues. Oops. 1 second. I think it's here. Yeah. Okay, let's take a look at this one here. So this is an actual image of these robots. So this is how one of them is moving. Again, this is not the nanoscale 3D printer, so you can see that the features aren't very fine, but it was fast and cheap. That's why we went with a little bit rougher edges. So we characterize basically the motion of each robot first. Now let me go a little faster here. And then we change the vibration conditions, right? We're changing the amplitude and the frequency. And then again, this is a measurement result. So we can see that there are some areas that the robot aggregate and they have higher density, right? And some areas they can have lower density. And we wanted to see, how does the mobility characteristics of the robots change based on their density. So we have these conditions that you can see. For example, some of them will have stable clusters of robots, and some of them will never form a cluster. And again, same robot, same ground. It's just that different vibration conditions that are being applied to them. So we looked at these different conditions, and we were basically able to control the clustering behavior of these robots by changing this external vibration parameters. So, it gets dispersed in condition number 3. And then you can change the vibration condition and get them to cluster, like in vibration condition number 1. I'm going to move, and these are like stable, basically clusters. And then let me spare you the rest of these are details on how basically you can control these robot swarms. All right, so now let me move to a little bit the applications of these 2D robots when they are scaled down. So one vision that we had was, can we, if we have a cell, right, a bacteria or a cell, can we use these little robots to puncture them, right, or to lyse them? So here is an image of a, not using a robot, but using mechanical lysis of a bacteria. And you can see that the internal, basically, fluid is just getting out. And our idea was, if we have, under a microscope, let's say we have a sample, can my little robots basically find out which cell is good and which one is not by some sort of a, biomarker or a sensing that they do, and then be able to basically lyse them or manipulate the cells, let's say. So we build these robots, and here we're just in the size scale showing how it compares to some of these unicellular organisms like amoebas, for example. So you can see that then the scale actually matches these amoebas, and we have these little tips, right, that can be very sharp, and they can penetrate into cells. So again, we're using magnetic fields this time, but it's not a coil around it. It's just a little compact electromagnet underneath our stage. And this robot, again, is moving. This one doesn't have any tip or blade. It's just moving forward, right, under simple magnetic field turning on and off. So pretty simple mechanism, unlike the brain one, which was more complicated. So we came up with different ideas. So these ones are kind of rocking, like a rocking chair, as you can see here, and moving backward and forward by turning the magnetic field on and off using different types of waveforms, right? For example, you can have a slow ramp and a steep decay, and you can tilt the robot to the front or to the back and therefore control the motion. So let me show a few videos here of these. We call them micro rocker bots. So here, basically, we're applying a sawtooth waveform and the little magnet underneath this stage and turning it on and off. And the guy is basically moving forward. We change the magnetic field conditions, the robot, without moving anything. Basically, the robot moves backward. And this is only, so this robot is 100 microns. So this is exactly the diameter of your hair, basically. So pretty small, again, truly microscopic. And then let me move this one. So here it's just showing that you can have two robots that move in opposite direction, just depending on how they are biased in terms of their tilt. And then finally, another best student award from the same graduate student who has done most of this work. So we added this blade, right, as I mentioned, and the idea here was that you can have the blade actually penetrate into a biological sample. And just as a proof of concept, we used a leaf, regular, not a very special leaf, and we showed that this little tip can actually penetrate into this leaf, as you can see this scanning electron microscope image. And if we show the video, this leaf is a more on smooth surface compared to the glass slides, which I showed previous videos. The robot can still move. It's a lot slower and maybe not as direct, but it can still go forward, and then now it's coming backward. And when it gets to the starting point, basically we apply a DC magnetic field, which makes the robot basically stand on its tip, as you can see here. right? So that's when this case is happening and the tip is getting engaged. So the idea is by just changing your magnetic field from sawtooth to a DC magnetic field, you can engage the tip or the blade of the robot to do a particular, function. All right, so let me summarize everything that I mentioned. So we basically, I explained a little bit about the different resonance modes of the legs of robots and how you can target a single robot or a single set of legs within a robot in a swarm of robots. And we showed these vibration-powered robots that just use simple piezoelectric transducers. We showed the smallest micro driller that is out there that can be used to drill inside a viscoelastic media, such as, in our case, a hydrogel or agar gel, but eventually brain tissue. And we added basically this payload, which was this pH-sensitive hydrogel that could have drugs inside it and release the drug when the pH of the environment is, let's say, more acidic and then more base. And we demonstrated mechanical capabilities such as tissue penetration, things that we are working on. And I think it's some of the exciting areas in the research field of microrobotics is integrating more sensors, microelectromechanical sensors on these microrobotic platforms, making them smarter, right? Not just mechanically puncturing into things, but maybe measuring something useful. And further miniaturizing it because we want to minimize tissue damage, obviously, as much as possible. So making them smaller, at least for the neurosurgery applications, is very helpful. And developing imaging modalities that are compatible with these robots, so in terms of the resolution and also, basically how quick can you get feedback on where the robot is, and eventually in vivo testing. Obviously we're not there yet, but for the micro driller application, in vivo testing would be the final product. And with that, I would like to thank some of the sponsors of our work. Again, so a small part of my group works on microrobotics. The rest of it works on 5G and communications. So these are all the sponsors and my PhD students and postdocs and collaborators. And most of all, I want to thank Puya and Kanoon for inviting me. This was a pleasure to be giving a talk here. And I want to thank everyone for joining this. I hope you all enjoyed it.